Okay, so it's 8:30, so let's go ahead and get started today. Good morning, everybody. How's everybody doing today? Besides tired, I know everyone's tired. It's the last week before Thanksgiving, so it's I think this is one of the hardest weeks to get through in the fall semester, just because we've been going at this for so long without any real breaks. So to have Thanksgiving on the horizon next week will be good. Okay. So there's homework that I assigned last week. So so that should be due on Sunday, I believe. Yes, it'll be Sunday, 11:59. So I wanted it to be due before the Thanksgiving break started, just so that you guys don't have anything to worry about for this class for the Thanksgiving break, and I can have the Thanksgiving break to grade it as well. So that's gonna be due then. So you should have enough to do problems 2 and 3 on the homework right now, and then problem 4 you should be able to do probably after today. Because that only covers just a small part of pipe flow. So that's going to be the subject for today, which is flow in pipes, which is a really important part of fluid mechanics, especially if you're an engineer. Okay. And so the other thing I wanted to talk about was the midterm. So I finished grading those on Wednesday, and so you should see your grades and you should see my feedback for your midterms on Canvas. And so just to let you guys know, so the average on the exam was pretty close to the average on the first exam. It was about 80%, so about 40 out of 50 was the average. Okay. And so it's looking like you guys are doing really well with this class. So I don't expect there to be any kind of grade adjustments at the end. And so unless something drastic happens on the final. But so far in this class, you guys have been doing great. So it's I think whatever grade that you have right now for the class, you can kind of expect that, if you kind of keep up the same performance, that's going to be, your final grade. But of course, the final exam is worth about 40% of your grade. So there's definitely a lot of room to to improve your grade for that as well. Okay. Okay. Any questions on anything before we get started today? Okay. Okay, so the subject for today is going to be pipe flow, or more specifically, we're talking more about viscous flow in pipes. Okay?
I don't think for me, I don't care, but for the fact that
your family,
my family,
I was around your whole freaking family. Yeah.
Oh. Brian, I think your mic is on. Okay. So last week what we covered was dimensional analysis. Yeah, no problem. Yeah, I just didn't want to listen in on anything private. So this week, we're going to cover kind of I call this kind of like a really important application of fluid flow. So we're not learning like a new concept or like a new, equations of motion. We're kind of applying that to a very specific situation, which is flow in pipes. Okay? I think this is kind of a chapter where like we really start to think about fluids from like an engineering point of view. Because up to this point in the class, we've been learning things like conservation laws, fundamental equations and things like that. So that's kind of like almost like it's all very heavily theory based. So it's almost like up to this point, it's almost like we've been taking just like a physics class. But engineering is not about. I mean, the physics, of course, is really important. But we as engineers, we always want to apply this physics to something that's kind of realistic. And I think this chapter really does that really well. Where like we're going to be looking at kind of real pipe situations where you can apply this knowledge to that. Okay. And we look at pipe flow specifically because this is an extremely important part. Is if you're going to be an engineer that works with fluids, you're probably going to work with pipes for under some capacity. Okay. And so just some applications that you can think of off the top of your head could be like all the pipes that run through your your apartment or your house. So like this is a flow of water through like a faucet. Okay. So that's where pipe's going to be. HVAC, so your heating and your air conditioning and ventilation, they all use pipes but that's for air, not for water. Okay. If you work with like I think at the beginning of the class we talked about the Alaskan oil pipeline, so big pipelines like that, those are big pipes, right? Right. There's even biological examples like just flow in your body. So your blood vessel is basically like a pipe, right? And a lot of these materials can be applied to that as well, right? And other things, like your motor oil and your engine, those travel through pipes, and many more. So the examples of pipe flows in engineering are very numerous and way too many to list in a class like this. HVAC stands for heating, ventilation, and air conditioning. So basically, the airflow in buildings. Yeah. Okay. And so in this unit, we're basically going to be combining two things. So we're going to be combining, what I call like analytical methods, which are, solving equations for certain quantities based on first principles. So actually, we'll see Bernoulli come back. So Bernoulli is probably the MVP of this fluids class. So we use him quite a lot, and this is no exception, right? And we're also going to make use of empirical data. So this is going to be dimensional analysis as well. So it's going to be combining kind of two of those things, and we'll see how they kind of combine to help us analyze these problems, right? All right, question. So the question is, do we consider air as a viscous fluid? So yeah, actually we do. So air has very low viscosity, but the thing is with pipe flow is that the diameters for these pipes are very small relative, and so if you think about airflow as like air over an airplane, that's a very vast open space. So in there, the viscosity plays a very little effect. But when you have these kind of very small confined spaces, like inside a pipe, like even the smallest viscosity, or the fluid with the really small viscosity is still going to have an effect there, just because the spaces are so confined. So in this case, we do consider air as a viscous fluid. Yeah. Mm-hmm. Great question. Okay. And so the reason we kind of need to take this kind of two-pronged approach with both analytical and empirical is that even though we have this kind of seemingly very simple situation of flow in a pipe, it can have some very complex effects that are basically they're basically impossible to capture just from equations alone. So because they're so complex, we need to rely on this empirical data in order to capture these quantities. Okay? Okay. And so we're talking in detail this week about turbulence, which is, it's an important phenomenon in all of fluid mechanics, but it plays a really big role in pipe flow as well. Okay. And so just to kind of give you an example of kind of a preview of where we're going, we're going to be looking at systems that look like this, right? So let's say that we have an inlet pipe. Let's say that we have kind of an elbow here to kind of change the direction, right? We have another pipe here. Let's say that we have a pump. And so we have a pump there that's going to add energy, right? Let's say that we have another kind of housing here. And so we have another thing that's going to split the flow. So we have a T intersection. And we have a curved X section of pipe. And let's say that we have a valve, right? I'll define all these things, later as we get to them. But, just to kind of give you just a preview of where we're going. So, this might be kind of a simple system. So like here you have like straight sections of pipe. You have here, which is like an elbow. This is like a pump. This is a T-split. And then this guy is like a valve, okay? And so we'll be looking at, specific, piping configurations like this and seeing how they affect the flow and how we can actually, do calculations with these guys, okay? Okay, are there any questions on this before we move on? Okay, and so the first thing that we're going to talk about is the difference between laminar and turbulent flow. So everyone's probably heard the term turbulence before. So you probably, if you've ridden in an airplane in any capacity, you know, you're familiar with the concept of like if the plane is going through turbulent flow, then it's kind of like, you know, you're going through you know, like a theme park ride. The plane starts to shake, right? And so what that refers to in an airplane is that, you know, when the plane is going through turbulence, what that means is that the air currents around and, you know, and the air patterns around the airplane are really chaotic, and they kind of almost like bully the airplane and kind of make it like rock and stuff like that. Okay. And so turbulence is not just unique to just airflow. You know, we can use turbulence to describe you know, just general fluid flows and how they behave. Okay. And so these terms right here, when you talk about laminar and turbulence, what they really describe is kind of how orderly, or, you know, how well behaved the fluid moves. Okay. Okay. So generally what we see is that as the velocity of the fluid increases, the flow patterns become more chaotic. Okay. Okay. And so basically, the faster you go, the more chaos that ensues. So, you know, if you're in your airplane and you know, and the plane's going against like a really heavy headwind, so there's like, you know, a drift, you know, of air that's going past you, you know, that's very likely that the flow there is going to turn turbulent, and you're going to feel that. Okay. Okay. So the very first person to, so I don't talk about, you know, history all that much, because it's I don't think it's that important in the grand scheme of things, but this is an important one. So this idea of turbulence was first observed by this guy named Osborne Reynolds. Okay? So you've heard Reynolds before, so his name is attached to a lot of things in fluid mechanics, because he did a lot. And so the experiment that he did was that he had a pipe. Right? And then in the middle of the pipe, he had kind of a little injector. Okay. And then from this injector, he was releasing some like food coloring or some dye. Okay. Okay. And so in this pipe, you know, we have flow that goes in this direction. So the flow is basically going to be carrying that dye downstream. Okay. And so what he observed was that depending on how quickly he moved the flow, or how you know, how fast the flow was, he observed different patterns for the dye. Okay. And so let's go over the case for low velocity first. And so I'll have low velocity in red. Okay. And so when he used low velocity, what he found was that the dye kind of stayed in just a single line, just like that. Okay. Okay. And so at low velocities, you know, the dye didn't really go out and explore all that much. It kind of basically just stayed in you know, within the same kind of line as which it came out from the you know, from this little injector thing right there. Okay. And so if you look at pictures from the experiment, you had kind of a very nice orderly line. So it was bold because, you know, the dye was in there. It was all concentrated into that single line. Okay. But then as he ran his experiment and he increased his velocity, so let's say that now he's under medium velocity. Okay. In medium velocity, you know, what he expected was that, you know, I would still see this dye streak, but it would just move faster down the pipe. But he noticed something that he didn't really expect. So as he increased the velocity, not only did the dye streak move faster down the pipe, it also started to spread out to the other areas of the pipe too. Okay, so it started to look like this. Okay. And so compared to the original dye streak, this one was spread out, throughout the pipe. So it wasn't no longer just staying in this very narrow column. It was starting to spread out to the confines of the whole pipe. Okay. And then as he increased this velocity even more, right? So let's say that he increased it to something that's high. This spreading got even more pronounced. So then we got something that looks like this, where the dye started to diffuse across the entire pipe. Okay. Which was very strange to him because the flow that he was putting in was only one direction, right? So he was just putting flow from kind of the left side to the right, and the flow field should look just perfectly horizontal. And so if that's the case, why was he getting this kind of spreading right here? And the spreading was due to this phenomenon that he just observed known as turbulence, okay? All right. And so I'll draw kind of another picture to illustrate turbulence on the next page. But before we do that, are there any questions on this? Okay. Right. And so from this experiment, he was able to basically come up with two different ways to kind of describe a fluid motion. Okay. So let me draw two pipes here. Okay. In the first case, which we called laminar. Okay. Under laminar flow, the flow waveforms are very orderly. So they kind of stick to a very orderly pattern. Okay. And so as an example of this, let's say that we draw the streamlines and they kind of look just like this. Okay. And so they all kind of just follow the same path, and they're just kind of like nice little soldiers in a row, okay? On the other hand, as he increased the velocity, what he started to notice was turbulence. And turbulence, for lack of a better term, because to be kind of real with you guys right now, we still don't really understand turbulence all that much, despite many years of research. We characterize turbulence as just kind of chaotic flow. So the flow, instead of having nice orderly streamlines, what we have on the left, it literally just looks like like your 3-year-old cousin just started scribbling onto the paper, right? And that's not that much of an exaggeration. So chaotic turbulent flow is really chaotic like that. And you can see here that we have flow streamlines that not just go in a straight line, but they travel to other parts of the pipe, which is how he was able to observe that spreading of the dye column. Yeah, chicken scratch. Yeah, like your doctor's signature. Yeah. Okay. And so now the question is, how do we determine, if we have laminar or turbulent flow? Like, yes, like we can kind of look at the flow like this, but what Reynolds wanted to do was, without having to run like a fancy experiment like he ran, he wanted to know if there was a way to determine, whether a flow was laminar or turbulent. And so he was able to come up with a way, and we actually saw this last week. Right? And so the way that he was able to determine whether a flow is laminar or turbulent was he came up with this number, which he named after himself, called the Reynolds number. Okay. Okay. And so let me define all the quantities here. So this rho right here, this is density. Okay. This V is velocity. D, in this case, D, so we'll see Reynolds number come up in other applications. So D can be any length. So we often call D the characteristic length of the flow. So it's just any kind of length scale that characterizes it. But for this experiment, D is going to be the diameter of the pipe. Okay. And then mu, of course, this is going to be our dynamic viscosity. Okay. All right, so question from the chat. So does turbulence still go in one certain direction? Yes. Yeah, so that's actually a really good point. So there's still some order to the chaos. So it's not just pure chaos, right? So turbulence, you'll still have kind of a net flow rate, in the direction that you want. It's just that there's going to be a lot of turbulent fluctuations. So if you take fluid mechanics at the graduate level, that's kind of a big subject that we talk about, is that for turbulence you can kind of break it up into what is typically called the mean flow, which is kind of like the bulk motion of the fluid. So you still have fluid that goes generally in this direction, but you also have a lot of what we call turbulent fluctuations, which are kind of what cause all this chaotic motion. But yeah, it's not just pure chaos. It's not that you reach turbulence and then just all hell breaks loose. So there's still some order. It's just that there's a lot more chaos than the laminar flow. Yep. Mm-hmm. Okay. And so what Reynolds found was that if you compute this Reynolds number, and your Reynolds number was less than 2100, then this gives you laminar flow. Okay. And then if you compute your Reynolds number and it's above 4000, this gives you turbulent flow. Okay. And then if you're in between, this is known as transitional flow. So transitional flow, it's like medium chaos, I guess you can kind of say. So it's not as chaotic as turbulence, but it's still more chaotic than laminar. So there's a more kind of precise definition of this, but it's hard to really get into that without really diving into turbulence, which I don't really want to do, because it's kind of a rabbit hole that kind of goes really, really deep. Okay. Okay. And so remember what
Professor, is that,
oh,
sorry, is that 2100 is less than RC is less than 4000?
Yeah, yeah.
Like,
It's so if the Reynolds number is between 2100 and 4000. Yeah. Mm-hmm. Yeah. So remember what the Reynolds number represents. So the Reynolds number was one of our dimensionless numbers that we talked about last week, and it's a ratio of inertia on top and then viscous forces on the bottom. Okay. And so what you can basically say is that for a fluid flow, as the inertia forces start to dominate, so as the velocity starts to go up, or say you have a heavier fluid, so you have a higher density or you have a higher length, right? So as inertia starts to dominate, then you start to get more and more chaotic flow, okay? And so generally the way that Reynolds number goes up is the velocity goes up, because usually the density for a fluid is relatively fixed. And so the only way that you can change the inertia is if you just increase the velocity. And so what you generally see is that as the flow gets faster and faster, then the Reynolds number gets higher and higher, and then you get more and more turbulent, okay? So one other note that I want to make is that, we'll see Reynolds number after the Thanksgiving break too, but under a different context. And so depending on the context, these thresholds right here, these thresholds are going to be different depending on the situation. And so these thresholds of 2100 and 4000, this is specific to just pipe flow, because that's kind of the subject for this week. But when we start to go over like boundary layers and external flow after Thanksgiving, these thresholds are going to be different. So I just want to kind of want you guys to keep that in mind. So after Thanksgiving, when I say, Reynolds number has to be greater than 10 to the 5th to be turbulent, I want you to think, it's because they're in different situations, okay? And so these numbers here were very much experimentally determined. So like they go pretty arbitrary. So and the reason for that is because these were just kind of measured from experiments, not really from first principles, okay? Okay, any questions on this? Okay. Okay, and so let's see how we actually start to use this in pipe flow. So if you're following along with the lecture notes, there's a big section of the lecture notes that I'm skipping, and I skip it every semester, so you guys aren't being shortchanged, because I want to get to kind of the more practical thing that you can use for your calculations. Okay, and so if we kind of assume at this point that the flow in a pipe can be either laminar or turbulent, there's a way that we can actually use that to perform useful calculations, okay? Okay. And so at this point, I'm gonna move on to the section called fully turbulent pipe flow. Although we'll have situations, or we'll have ways to deal with laminar flow as well. But it's going to be based. I want to do it all in kind of the same methodology. So the sections that I'm skipping is if you can assume that it's laminar, there's certain equations that you can use, but those equations are only relevant when you're in laminar flow. But these turbulent flow equations can be used for both of those. Okay. And so let's talk about why turbulence is so interesting in fluid mechanics. So I wasn't kidding when I said earlier that says we still don't really understand turbulence that well. So researchers, it's still an extremely hot topic research topic for fluids, and no one has really come up with a great way to kind of characterize it. There's been kind of a lot of work, and they work well in certain situations, but there's no like unicorn, as we like to call it, or good ways to really describe it. But we do know some kind of qualitative features of turbulence that that are relevant not only for fluids but also relevant for other fields as well. Okay. And so the first one, and this is going to be relevant if you're taking 407 next semester, which is heat transfer. And so if you have turbulent flow, because of the chaotic mixing or the chaotic motions, this enhances mixing and heat transfer. Okay. And so because in turbulent flow you have kind of those crazy turbulent fluctuations, that's going to just naturally carry stuff and mix stuff a lot better than laminar flow, where everything just kind of goes in the same direction. Okay. And so this is actually really useful because sometimes, as you'll see in 407, there are cases where you want to enhance the heat transfer. You want to have more heat transfer in a situation, and turbulence is one way to achieve that. Okay. And so one kind of a quick example that you can think of is that if you have coffee, and if you're like me, you have to like kind of drench it in coffee mate in order for it to taste good, right? And you want to mix your coffee mate or your creamer with your coffee. You're not going to do nice, slow, grand mud motions, right? You're going to take that stir and you're going to stir the crap out of it, right? And so as you're stirring the crap out of it, you're basically creating a turbulent flow, right? Because naturally that if you stir really fast, that turbulence is going to mix the creamer in better with your coffee than if you just did it slow, right? Okay, so that's kind of a nice kind of heat transfer application for that. So you'll definitely see that a lot more in 407 if you take that next semester, right? And so the other thing that turbulence helps with is that turbulence, or I guess this is a bad thing, and so turbulence will also increase the pressure drop along the pipe. Okay. Relative to laminar flow. Okay. And so if you have turbulent flow, remember we kind of talked about pressure drop as a way to kind of characterize how much energy or how much force it needs to drive a flow. And so if you have turbulent flow, it's generally going to be more inefficient in terms of your energy. So it's going to take more energy per fluid in order to drive turbulent flow. Okay. And so one other thing that I want to talk about is that when you compare turbulent flow and laminar flow, turbulence increases the drag on a solid body. Okay. Okay. And it increases what's called a very specific kind of drag called a friction drag or viscous drag. Okay. Okay. And so we'll talk about this more after Thanksgiving, but I thought I'd just kind of mention it right now. So, turbulence, even though we don't really fully understand it yet, we do know some of its effects on certain things, at least from an engineering point of view. Okay. And so with those in mind, we can start to, start to use this in some kind of analysis. Okay. And so before we begin, I want to bring back Bernoulli for probably, the fourth time this in this class, but it's really useful, right? And so I'm going to put Bernoulli in a different form. And so I don't think we cover this explicitly, although some of you guys have seen this in the notes. But this is going to be more useful for our calculations here. And this is going to be the Bernoulli equation in head form. Okay. And so what's unique about this form is that we've manipulated the equation such that every term here has units of energy per weight. Okay. Okay. And so basically every term here has going to have units of like joules per Newton, something like that. Okay. Right. And so our Bernoulli equation looks something like this. Okay. And so we're going to have P out over gamma. And so remember, gamma is specific weight, so that's density times gravity. Okay. And to that, we're going to add B out squared over 2g, so that's our kinetic energy term. Oops. Next, we have our height term. Okay. And so that's just z out. So of course, that has dimensions of length, but length also has the same dimensions as energy per weight. Okay. And so they end up having the same dimensions, but they have kind of different interpretations. Okay. Right. And so this is going to be equal to the same quantities at the inlet. So you have P in, pressure in, divided by gamma, plus V in squared divided by 2g, plus Z in. Okay. And so that's, those are the standard Bernoulli terms. But since we're talking about energy here, we have to also include terms for shaft work and also for losses, okay? And so I'm going to give this, the shaft work, I'm going to give that a term H sub S. Okay? And then the losses, I'm going to give the term H sub L, okay? And so this right here is shaft work. And this right here is head losses. Okay. So remember, shaft work is if you have like a pump or a turbine in your flow where you have a device that's specifically designed to either insert energy or take away energy from the flow. And then HL is your losses. So that's, energy losses that are due to dissipation or viscosity. Okay. And so the focus for this unit in pipe flow is actually going to be this guy right here and how we actually quantify this. Okay. And so I think previously when we saw this for conservation of energy, I kind of just gave you the losses, but now we'll actually have ways to actually compute this using some experimental data that people have done in the past. Okay. Okay. Are there any questions on this? Okay. Okay. And so let's talk about these head losses a bit more. Okay. Okay. And so remember, so these head losses, what they represent is a viscous energy loss in pipe flow. Okay. And so as you can imagine, as the pipe flows, as the fluid flows through the pipe, it's going to be rubbing against the sides of the the sides of the pipe, right? And so just like, when you rub your hands together and you have heat loss from friction, as the fluid rubs against the sides of the pipe, it's going to incur some energy losses, okay? And so there are two categories of losses that I want to talk about. And so the first one is called major losses. Right? And so major losses are defined as, energy loss as the flow goes through straight segments of pipe. Okay. Okay. And so just by going through just a straight section of pipe, you're going to have some energy losses there. And so the other thing that we'll talk about is minor losses. Okay. And so minor loss is any energy loss that goes through basically everything else. Okay. Okay. And so remember from the figure at the beginning, we had things like bends, like L bends, T intersection valves, flow splitters, pumps, and stuff like that. So basically, everything else will be characterized as minor losses. Okay. All right. And so once you compute the major and the minor losses, the total head loss is just going to be the sum of these two guys. Okay. And so what we're going to do next is we're going to learn how to actually compute these two these kinds of losses. Okay. And so we'll cover major losses today, and then if we have time, we'll go minor losses later. Okay. And so one thing I want to talk about, before we begin, is that this naming convention is terrible. Okay. This is probably one of the worst naming conventions in fluids because when you think of major and minor, you think that major losses are going to be bigger, right? And so that's not the case at all. So it's the major and the minor here have nothing to do with their relative magnitudes. Okay. And so we're gonna see situations where your major loss is actually extremely small, but then your minor losses are going to be really big. And actually, this happens a lot in practice because actually, even though we call them major losses, there's usually not that much energy loss in there compared to the minor losses. So if you're doing homework problems and you get a minor loss that's like 5 times higher than a major loss, don't panic. That's what it's like in a lot of the times, just because it's and the naming convention that they chose for this is terrible. And it's even more terrible because it's not even named after the person who invented this. It's just that the person who named this was just kind of a bonehead and chose, kind of the worst naming convention for this. That's going to confuse fluid mechanics people for the rest of their lives. Okay. Any questions on this before we start going into major losses? Okay. All right, so let's talk major losses first. Okay, and so just like was mentioned before, the major loss has to do with energy loss associated with straight segments of pipe. Okay? And so, the way that we kind of characterize this energy loss is as a pressure drop. Okay? And so, essentially what we can say is that, because of these major losses, we're going to have a drop in pressure as we flow through a pipe. Okay. And so this characterizing this pressure drop is actually pretty complicated, because especially when you have turbulent flow. But we can come at this from a dimensional analysis standpoint. And so from dimensional analysis, what we found is that the pressure drop, or delta P, is equal to a function of the following parameters. Okay, so it's a lot. So we can say that the pressure drop is basically going to be a function of the velocity v, the diameter d of the pipe. This right here is the length of the pipe. So depending on how long your pipe is. Okay. At the end here, we have mu and rho, which are viscosity and density. Okay. And so we have a new guy joining the party right here. Okay. And so what this guy represents here is the surface roughness. Okay. And so what that represents is the fact that when you have flow in a pipe like this, the pipe is not going to be perfectly smooth. Okay, so you're going to have a little roughness on the surface. And so that's almost always going to be there, because it's almost impossible to eliminate this this roughness. You have to use very precise machining methods to at least minimize this. Okay? And the way that this roughness is characterized, it's characterized as the height of this kind of imperfections. Okay? And so this epsilon here, this has a units of length. Okay? In other words, it's the height of the roughness. Okay. And so if you're curious about what typical surface roughness values are for a pipe, this is tabulated in table 8.1 in the book. Okay. And so in table 8.1, what you'll see is that if depending on what type of material your pipe is, they'll give you kind of typical values for these surface roughness. But again, this is something that you can also look up on online databases. Or a lot of times, if you buy a pipe, then it might be kind of the specs for that pipe as well. So, this is an important thing to know. Okay. And also, just for your guys' awareness that it's the roughness that you usually see in these table values. These are for a new pipe. So, generally as you use a pipe, the pipe surfaces, they generally get corroded, or stuff gets or gunk gets kind of put on there too. And so generally what happens is that the surface roughness increases with time as the pipe kind of gets used up and wears out. Okay. Okay. And so at this point, we can go through the whole song and dance. We can go through the method of repeating variables and find out what this pressure drop is. But for this case, it kind of takes a while. And so there's actually a much more simple formula that we can use and make use of some experimental data that we can use to characterize these losses. But I'll do that on the next page. Okay. So before we get there, are there any questions on this? Okay. Okay. And so instead of characterizing this this pressure drop for every pipe, we're basically going to make use of some experimental data. Okay, and so the way that the experimental data is formatted is that it's formatted in terms of this thing called the friction factor. Okay. And so the symbol for the friction factor is given by F. Okay, and what this friction factor represents is basically it's a non-dimensional number that represents how much viscous loss is going to be in a section of pipe. Okay. And so once you have the friction factor, you can actually use that directly to compute the major losses. Okay? And so this is going to be the important formula here. And so once you have the friction factor, your major losses is given by the following formula. Okay? And so your HL major is going to be F, which is your friction factor. Okay? And then to this, we're going to multiply the ratio of the length of the pipe over the diameter. Okay? Okay? And then to this, we're going to multiply a kinetic energy term. Okay? So remember, V here represents the velocity. Okay? G is just gravity. And then once we have all these together, we can compute the actual head losses that are associated with the major losses. Okay? And so most of these things you can get easily for a problem. So a lot of times you know the length of the pipe, you know the diameter, you know the velocity, and you know gravity, of course. And so the only question is, how do we determine this guy? Okay. And so the friction factor, this is what someone did back then was they ran basically a ton of experiments and they computed this. And so the way that we're going to look up this friction factor is we're going to look it up from a chart. And in particular, the chart is called the Moody chart. It's not a Harry Potter reference. The guy was actually named Moody. Okay, and so this is if you want to look up the Moody chart in your book, which I highly recommend. So don't use the one that's in the notes because it's drawn poorly. And so this is going to be figure 8.2 in the book. 8.20, sorry. Right. But the Moody chart is famous, so actually you can just Google it, and then you'll come up with probably a much better version of that as well. Okay. And so on the next page, I'm going to draw you kind of a poor representation of the Moody chart, just so you can kind of know what you're looking for. But again, don't use the one that's from the notes, because the one from the notes is not that precise. So you want to use the one that's either online or in your textbook. Okay. Before we do that, are there any questions on this? Okay. Okay, so let's draw the at least an approximation of the Moody chart. Okay. Okay. And so the Moody chart looks like this. And so we have on the y-axis on the left, we have the friction factor. So that's how you're going to look up, your F. Okay. On the x-axis here, we have Reynolds number. Okay. And it's actually given to you in a log scale. Okay. Right. So it's going to be given to you in orders of 10. Right. So we have 10 to the third, 10 to the fifth, 10 to the sixth, 10 to the seventh. It actually even goes up to 10 to the 8th. So Reynolds number can get really high. Okay. And on the right here, we're going to have the ratio of epsilon over d. Okay. And so remember, epsilon represents the surface roughness of your pipe. Okay. Right. And then from this, you should see things that look like this, basically. So you should see kind of a bunch of lines that kind of go like this. Okay. And so what you'll see next to this is that next to each of these, you should see a number. So you see like this one be 0.05, this one might be 0.02, this one might be like 0.01. Okay. This one probably is like 0.001, it's probably 0.0005, this 0.0001. Okay. And so I'll let you know what those numbers mean in a second. Okay. And on the left-hand side right here, we have kind of a nice line like this, right? That looks like that. Okay. Okay. All right, so there's a lot going on with the Moody chart. So let's kind of take it apart kind of step by step. First thing I want to talk about is kind of this separation in between these two, okay? And so on the one side, you have kind of the straight diagonal line going down. And so on the left right here in blue, you know, if on the left side of the graph, you know, that's where our Reynolds number is really low. This is for laminar flow, okay? And so if your flow is laminar, you know, you're gonna follow that curve. And on the right here, this is for turbulent flow. Okay. Okay, and so you can see kind of the separation between them based on their Reynolds number. Okay. Okay, and so let's talk about how we actually use this. Okay. All right, and so the first thing to compute is we need to compute the Reynolds number. Okay. And so once you compute the Reynolds number, you know where you're going to be horizontally on the chart. Okay. And so, you know, based on your Reynolds number, you're going to pick out a place, and that's going to tell you whether you're going to be laminar or turbulent. Okay. All right. So the second step is that if you're turbulent, you need to compute this ratio of epsilon over d. Okay. And so this epsilon over d, this is the ratio of the surface roughness over the diameter. Okay. And so based on that, your computed value of epsilon over d, you're going to pick one of these curves here on the left. Okay. Right. And so let's say that you computed an epsilon over d, and that's equal to 0.01. Okay. And then in that case, you know, you're going to follow this graph right here. Okay. Right. And so in step 3, once you have your Reynolds number and once you have your epsilon over d, you know, all you're going to do is just read off the friction factor from the graph. Okay. And so let's say that we had a Reynolds number of 10 to the 6. Okay. And so we're going to follow up the 10 to the 6 up to the curve that we want. Okay. And then this location right here is going to be associated with the friction factor that's going to be over there. And so whatever we read off the graph, that's going to be the friction factor we're going to use for our problem. Okay. Right. So the question in the chat is the D still our characteristic length, or is this purely for pipe? So this is purely for pipe. So the D is always going to be the diameter of your pipe. Yep. Yeah. Good question. Okay. Are there any questions on this? Okay. Okay. And so if you have turbulent flow, you know, you're going to use the Moody chart for your problems. Okay. You know, I made that kind of section on the left there for laminar flow. But there's actually an easier way to compute the friction factor for laminar flow. Oh, question in the chat is, how did I know to use 10e to the 6? And so that was just an example. So we'll do an example where we'll actually compute the Reynolds number, and that'll tell us where to be on the chart. But that's going to be whatever Reynolds number you compute for your problem. Yeah. Mm-hmm. Okay. Right. And so for laminar flow, remember this happens when your Reynolds number is less than 2100. Or, you know, for special cases, which we'll do an example in a second. Okay. And so if you have laminar flow, And so if you have laminar flow, there's actually an easy formula for the friction factor. And so that's going to be 64 divided by Reynolds. Okay? And so you have Reynolds number, you don't even have to bother with the Moody chart. Or if you have a laminar flow, you don't even have to bother with the Moody chart. You just plug it into this formula right here. Okay? And that's only for laminar. So if your Reynolds number is above 2100, or if you can assume that the flow is turbulent, you're going to have to use the Moody chart for that. Okay. Okay. And so number two, even despite the Reynolds number, sometimes it's possible to induce turbulence. Okay. Okay. Because normally you don't get turbulence until your Reynolds number passes a certain threshold. But sometimes you want to get some turbulent effects without having to increase the velocity. So there are some things that you can do, like you can put a tripwire in the flow to kind of create that chaotic motion without having to increase the velocity all that much. Okay. And so if you do come across a problem where it basically says that the turbulence is induced, or the turbulence is tripped, there's a special line in the Moody chart for that as well. And so I didn't draw it there, but basically if this was the case, what you're going to do is you're going to follow the curve for wholly turbulent. And so if you look at the Moody chart from the textbook, you should see that there's a curve called wholly turbulent, and that's basically what it means, is that that's turbulent flow that's been induced or tripped. Okay. Okay. And so once that friction factor is found, once your friction factor is found, you could use this to compute your major losses. Okay. And then once you compute your major losses, you can plug this back into your extended Bernoulli in order to compute pressure drops or anything else. Okay. Right. And so in the case where your velocities are going to be the same and your height's going to be the same, so this is purely just for a straight segment of pipe that's horizontal. So your velocity terms are going to cancel out, and your height terms are going to cancel out. We have a formula for the pressure drop here. Okay? And so this is a special case. So most of the time, what I want you guys to do is to actually plug this back into extended Bernoulli. But for the cases where all the velocities and the shaft work is 0 and the height difference is 0. In this case, is that you can have a formula for delta P, and delta P is going to be F times L over D, okay, times rho V squared over 2. And so this is a special case. So most of the time I want you to plug into the extended Bernoulli, but even when you do plug into extended Bernoulli, this is what you should get. Okay. Any questions on this before we do an example?
You said that this equation was a special case for straight segments of pipe?
Yeah, it's for straight segments where there's no height difference. So this is what I basically did is I plugged into extended Bernoulli for you, and then the velocity terms cancel out, and then the height terms cancel out as well. Yeah. Yeah. So if you have those cases, you can use this formula, but in my opinion, I think the safer thing is just to plug into just extended Bernoulli. Okay, so let's do an example. Okay, And so this example, let's say that we have a pipe with a diameter of 4 millimeters. Okay. And let's say that the material that's used for the pipe is called drawn tubing. And so we're going to use that information and we're going to look up its roughness from the table. Okay. And let's say that the average velocity in this pipe is going to be 50 meters per second. Okay. And so normally, 50 meters per second is actually huge. And so, if you know how long a meter is, multiply that by 50, and then the fluid is going to travel that length of 50 meters in 1 second. So this is really fast. So, what you'll find from this is when you compute the Reynolds number, it's going to be ginormous. Okay. So so normally this flow is going to be turbulent. Okay. But let's just assume, just for this problem, we are really good fluid engineers, and even though we have this really high velocity, we have the ability to keep this flow laminar. Okay? And I'll just call it magic because there's no other way to describe it. But it's mostly just to kind of show you, how to do the calculations with the laminar flow. Okay. And so remember, laminar is not a characteristic of the speed, but it's a characteristic of how orderly the streamlines are. So, just by some magic, even though we're moving this fast, we're able to keep the streamlines, very nice and straight and orderly. Okay. Okay. And so if our length of tubing is 0.1 meters, okay, let's compute the pressure drop in this pipe. And so let's compute the pressure drop if the flow, in the first case, we'll take the case where the flow is laminar. And then part B, we'll do the fully turbulent case with the Moody chart. Okay. Okay. And so we can also assume that there's no height difference in the flow, and that if the diameter is constant, then the velocity is not going to be different. So we're going to use the formula that we had kind of up above. Okay. Okay. All right. So let's do part A. Okay. And so if we go back to the formula on the previous page, in order to compute the pressure drop, we're going to need basically every variable in this expression. So we need to know the length, we need to know the diameter, we need to know the density, we need to know the viscosity, we need to know the velocity, and we need to know 2, and 2 is fine. Okay, and so let's add some additional variables here. And so let's say that we have a density of 1.23 kilograms per meter cubed. Okay, and so this is the density of air. Okay, and our viscosity in this case is going to be 1.79 times 10 to the minus 5 Newton second per meter squared. Okay. Okay. And so that gives us most of what we need. And so the last thing that we need here is the friction factor. Okay. And so in part A, since we're assuming that the flow is laminar, we can use the following formula for friction factor. Right? And so for flow is laminar, we can say that the friction factor is just going to be 64 divided by the Reynolds number. Okay? And so in order to do this, we need the Reynolds number. And so the Reynolds number is going to be rho phi d over mu. Okay. And so we plug all the numbers in. Then we find that our Reynolds number is 13,700. Okay. And so if we plug that back in right here, what we get is a friction factor of 0.00467. Okay. And so now that we have friction factor, we can go ahead and compute the pressure drop. And so our pressure drop is going to be F times L over D times rho V squared over 2. Okay. And so we plug in all the numbers, and what we get is a pressure drop of 0.179 kPa. All right. And so as the flow goes through this pipe, you know, and by magic we can keep the flow laminar. You know, our pressure is going to drop by 0.179 kilopascals. Okay. All right. Any questions on this part here? Okay. And so that's the conditions for laminar flow. So laminar flow is pretty straightforward. You know, you just use that formula to compute the friction factor. But if your flow is going to be turbulent, you know, we have to use the Moody chart.
Quick question. The friction factor is a unitless term?
Yes, it has no units.
Okay. Thank you.
Okay. And so for turbulent flow, you know, we have to obtain the friction factor from the Moody chart. Okay. Right. And so we're basically going to follow the same recipe that we talked about before. And so the first step for that recipe is to compute the Reynolds number. Okay. And which we did in the previous part. So we know the Reynolds number is going to be 13,700. Okay. 2, we need to compute the ratio of the roughness over the diameter. Okay. And so that's going to be epsilon over D. Okay. And so we know D from the problem, so D is going to be 4 millimeters. Okay. And so at this point we need epsilon. Okay. And so if you look up from the table in the book for drawn tubing, we see that epsilon is going to be 0.0015 millimeters. Okay. This is from table for drawn tubing. Okay. And then once we compute this ratio, well, we see that this is going to be equal to 0.00035. 375. Okay. Okay. And so at this point, since you know the ratio of epsilon over D, you can use this and search for that value on the Moody chart. Okay. Okay. And what you'll find is that there's actually no curve for 0.000375. Okay? But there is a curve for 0.004. Right? And so this is close enough. So a lot of times when you're doing these problems, you know, you're not going to find a Moody chart curve that exactly matches your epsilon over D. And so you're just going to have to pick the one that's kind of closest to it. Okay. Okay. And so for this, you know, if we look up on the Moody chart and for this Reynolds number, what we get is a friction factor of 0.028. Okay. And so if we use this friction factor and we use it to compute pressure drop, and so pressure drop is going to be the same formula as before. So we have friction factor times L over D times rho V squared over 2. Okay. What we get from this is 1.076 kPa. Okay. And so what you can see from this is that if you have turbulent flow, and we compare this to our answer in part A, right? And so part A, we only got basically 0.18 kilopascals of pressure drop. And so we compare that to our answer in part B, which is 1.076. You can see that turbulent flow has a much bigger pressure drop. So basically to flow, fluid down the same length of tubing, at the same speed, it's going to take turbulence, over 5 times as much energy, or that's almost 6 times as much energy to basically drive the same flow. So you can see turbulence, is very inefficient. So because you have all that random motion, basically what's happening is that there's fluid that's basically colliding with the pipe walls basically all the time. And so because of that, you have a lot more energy losses than you do in laminar flow, where everyone just kind of flows down their own path. Okay. Any questions on this example here? Yeah. So the question in the chat is, what is that table from drawn tubing? And so, yeah, I wrote it down kind of earlier in the notes. Let me find it again. I think it's table 8.1. Let's see. Yeah, table 8.1. Yeah, so if you look up table 8.1 in the textbook, that's going to show you the surface roughness for different pipes. Yeah. Okay. Any more questions on this example here? Okay, so that's major losses. So for major losses, first thing, you always have to compute the Reynolds number, so that's always going to be important. Then depending on if you're laminar or turbulent, that's going to give you different formulas for your friction factor. Okay, and so with that, you should be able to do the homework problem now. So that gives you enough to do problem 4. Okay, and so since we have a little bit more time left today, I do want to kind of introduce the concepts for minor losses. Right. And so remember, minor losses, these characterize the energy losses through basically every other pipe component that's not straight. Okay. And so some examples that we talked about before are like bends and valves. Okay. That's because, as the flow goes through these devices, what tends to happen is that the flow kind of has to either change direction or go around to some components, right? And so even if you think of a simple case of like a bend, right? And so let's say if you have fluid coming in, right? So as the fluid comes in, it kind of has to basically run into this wall up here and realize that there's a wall. And then after that, it's going to curve into these directions. Okay? And so because we have that kind of collision with the wall, there's going to be some losses that occur from that. Because you have some kind of like, the flow here is a little bit chaotic, even for the most laminar flow. So because of these, because the flow has to change direction, that's going to incur some losses. Okay. Okay. And so just like major losses, we're going to compute things in terms of, heads. Okay? And so the formula for minor losses, where the major losses had their friction factor, minor losses have these things called the loss coefficient. Okay? Right, so it's going to be K times L times V squared over 2G. Okay? Where this guy right here, this is our loss coefficient. Okay. And so the loss coefficient, is it's going to depend on what type of device that you're going to be looking at. Okay? And so we'll get into that next time because we're out of time for today. But what we'll see next time is, based on what type of component you have, you can compute the minor losses based on this. Okay, so that's all we got time for. So thank you everyone for tuning in. I know it's the week before Thanksgiving. It's always kind of hard to get up for this, but I appreciate you guys coming out. Okay? So have a good day. So we'll see each other again on Wednesday, where we'll finish up these lecture notes on pipe. Okay. All right. So I'll see you guys on Wednesday.
Thanks, Professor. See you.
Thanks, guys. Thanks, guys.
See you, Professor. Have a good one.
Yep. See you too. Yep. Yeah. So I'll be in office hours in 15 minutes. Yeah, I'll see you in there. All right. Did you guys have any more questions? Okay. Sean, I'll see you in office hours, and then Rico, if you want to have any more questions, I'll be in office hours in a little bit.